5.2.2 is actually just what I wrote mathematically written in code. Just makes it easier. So we're defining functions, remember, and suppose we've got a function f, and we can get its function space out, because we set up functions like that. And so now we can make a Lagrange element on whatever cell is associated with this function space. And it's going to be degree 1 because our triangles are straight. By the way, if you interpolate back what I've just said, I've just told you how to make bendy triangles. So if you need to make triangles that are bent, for example, because you are solving a PDE on the surface of a sphere and you need to represent the surface of the sphere a little bit more accurately than as some sort of polyhedron, then you just use a higher order finite element space for coordinate. So you can have a quadratic or a cubic representation of coordinate. I think our current thinking is that if you want to build an ocean model, you need about cubic in order to be accurate enough. So, so here's our linear space though, and then we build a function space out of the mesh and the finite element space. And now we get to use what you did in chapter 4, what you might have finished doing yesterday or you might still be finishing. So this tells us for a particular cell what its nodes are. And if I know what the nodes are, then I can look up in the list of coordinates of the mesh what the vertices of the current cell are in node order. So the fact that I did this, so I could, in principle, just assume that this is going to be equal to the vertices in the right order and pull this out. And if my numberings coincide, I'll be fine. And if my numberings don't coincide, I'm in big trouble. So by doing it this way, I'm pulling out the correct set of nodes in the correct order. And so that gives me the coordinates of the vertices. And this gives me the corresponding node values in F. So the FIs that correspond to that.